Okay, so next we have Nirmal Raj from IIC Bangalore. He'll tell us about dark matter at neutrino facilities. So over to you.
All right, thank you, Amol, and thanks for inviting me, and thanks everybody for being here. Always a thrill to come to ICTS. I have a little bit of history here. So I actually got my job offer in this very room. I was sitting here when I got the email. It was actually Amol who approved my my hiring as well. Anyway, so dark matter and neutrinos have an intimately connected history, and they're often mentioned in the same breath, right? And in fact, 1% of dark matter, as we know, is made of neutrinos. So it's not very surprising that if you build a detector to look for neutrinos, you can do something with it to look for dark matter as well, some kind of dark matter, right? The possibilities of dark matter are nearly endless, so there must be something out there with which you can look for, there must be some way in which you can repurpose neutrino detectors to look for dark matter. And that's what I'm going to be talking about, focusing on a few ideas that I've thought about. In this talk, I'll be talking about how you can use certain kinds of neutrino detectors to look for scattering of dark matter in the halo, absorption of certain kinds of dark matter in the halo, and if you have friends of dark matter or some dark sector particles, how you could set up neutrons shining through a wall type of experiments. This is IPL season, so I have to show this, to basically look for neutron oscillations, very much in the spirit of neutrino oscillation. All right, so let's jump right into it. Here's a lightning review of dark matter. I'm sure you've heard many things about dark matter in this workshop and elsewhere. Dark matter is dark, it is non-luminous, it's unfriendly to light, doesn't absorb, emit, or reflect light. We know it is present all over the universe at every scale larger than the distance scales of dwarf galaxies. It makes up 5/6 of all the matter in the universe, which is what really makes it a crisis for physicists, right? And despite heroic efforts to unveil its identity, it stubbornly refuses to tell us what it is actually made of at a microscopic level. And we know it's there because it pulls on everything else through the force of gravity. And over the last few decades, we've amassed many different pieces of evidence for dark matter from astrophysical and cosmological data. Right? I'm not going to go through all these. I'm sure you've seen these or learned about these. Okay. Now, all the evidence for dark matter that we have, as I said, is via the force of gravity and astronomical in nature. But if you really want to know the microscopic identity of some unknown entity, you better get its particle physics fingerprints, right? That's how we know so much about the Standard Model. That's how we know so much about what the stable is made of, what are the interactions of the quantum fields that it's made of, and so on, right? And one of the best ways you could suss out the particle physics fingerprints of an unknown entity is to set up a scattering experiment. This is a lesson that we've learned over the past decade. It's probably Rutherford who started this grand program of scattering experiments to look for microscopic properties through scattering of alpha particles on gold foil. On a gold foil is how he discovered the presence of a tightly bound nucleus in the center, in the kernels of atoms. Scattering of X-rays is how Rosalind Franklin and friends unveiled the double helical structure of the DNA. Scattering in the deep inelastic regime using electrons and neutrinos is how we, discovered the partonic structure of nucleons, right? So, okay, scattering is really a very unignorable, important tool in a physicist's tool shed. So it's no wonder that people have set up many scattering experiments over the years to look for dark matter as well, in a process that I like to call the reverse Rutherford process, a reverse Rutherford scattering. Why do I call it that? Because in this case, the beam is unknown. Okay, the beam being the dark matter flowing in a sort of isotropic way. into Earth from the dark matter halo, and the target is a well-understood species such as a nucleus or an electron and so on. Okay, and by studying changes in the target due to transfer of energy and momentum, you could try to tell something about the intrinsic properties of this dark matter wind or dark matter beam that's coming in. For example, the scattering cross-section and the unknown mass of the dark matter particle and so on. Okay, and the ingredients that you would need to set up this reverse Rutherford experiment are the typical speed of the dark matter beam and how much dark matter there is, the mass density of dark matter that is flowing in, of the beam again, right? And thankfully, these we've known for a while. By measuring stellar motion, especially in the vicinity of the solar system on a galactic scale, we've inferred that the typical speed of dark matter is around 1,000th the speed of light, which is the typical speed of all the stars are in this position, okay, in the galaxy. And the density of dark matter is constrained to be around 0.3 GeV per centimeter cubed in particle physics units. That comes to about a couple of protons per teaspoon. Okay, so we fairly well know some of the properties of the beam with which we can do this experiment as well. Okay, of course I call it reverse Rutherford scattering, but the better known name for this is direct detection of dark matter, right? Because you're literally directly detecting this beam in the flesh by setting up some monolithic detector, right? So direct detection has been going on for about 4 decades now, maybe, yeah, 4 or 5 decades now, okay? And here is a typical parameter space in which the results are shown, the constraints are shown in the space of the cross-section for dark matter hitting your target, such as nucleons, versus the dark matter mass. These are the two unknown quantities when you are constraining the rate of the beam hitting your target, okay? And then this is one of the latest plots. Okay, the latest plot is obviously 2023 or 2024, but one of the latest plots, but they all have the same shape of the constraints. And today, experiments have gotten so big, so sensitive that with a straight face, we can say that you can constrain dark matter down to cross sections of 10 power minus 47 centimeters squared, which is a ridiculously small cross section, right? But that's how sensitive experiments have become. Okay, and if you want to interpret shapes like these with a broad brush, theory-wise, you could say that probably dark matter that is mediated through a Z boson, very much like the neutrino, probably that scenario is dead, because in that case you expect cross sections at around 10 power minus 39, 38 centimeters squared. But if the dark matter were to be, if the interactions are mediated by a Higgs boson, that door is still probably open. That is still, you can still. All right, now, if you stare at this plot long enough, you could ask yourself a question: is this all there is, okay, on this space? Can I extend this line all the way to the right? What about all the way to the up, right? Can I go to infinite cross sections and can I go to infinite masses? Or can I go to 0 masses and can I go to 0 cross sections, right? Now, we know, without knowing anything else, we know that cannot be true, because nothing in physics is infinite, right? There's always something that regulates. There's always some finite effect. So we'll see soon what that is. But one can ask, how would constraints look like if I were to zoom out on this space, and where would I actually draw the finite boundaries of my sensitivities with these kinds of experiments? Okay, so here's like a bird's eye view of the plot that we just saw. I've just shrunk the plot in the previous slide. And now we notice that the cross sections that I'm showing here are spanning around what, 40 orders of magnitude, and the masses that I'm showing are around 20 orders of magnitude. Okay, these 20 orders are where you expect dark matter to behave like a particle, right, as opposed to a wave or some macroscopic entity, right? And these are the range. This is the range in cross sections that happen to be probed by all the experiments that we've set up so far on Earth. Okay, so this is the space in which we will operate in the first half of the talk. Okay? Okay, so this is not such a relevant slide, but it's just repeating what I just said. We've been doing these kinds of experiments since 1985, so it's 4 decades. And of course, a large part of parameter space has been carved out. And how did it all begin? This is what I mean by intimately connected history with neutrinos. It was actually a proposal to look for coherent nuclear scattering of neutrinos, which has been finally done now with the coherent experiment with capital letters, right? It was actually a proposal for measuring that process by Drucker and Stodolsky that inspired Mark Goodman and funnily Ed Witten to propose a similar kind of experiment for dark matter detection as well, using coherent nuclear scattering. It doesn't have to be coherent, using nuclear scattering at least. Okay, so that is the grand beginning of the direct detection program of dark matter. And in their paper, they didn't draw this plot, but then you could pick out the numbers. They were thinking of a little sodium iodide crystal about a few centimeters in span, and using that crystal and using the energy sensitivities, if you were to plot what they are saying, this was the sensitivity that they were proposing on this parameter space. Okay, so even back then, it was not just the WIMP region of around the ultraweak scale that their experiment would have been sensitive to. Even back then, even with the very first proposal, you would have carved out many orders of magnitude in masses and cross sections. Okay, so that was the beginning. But today, if you were to plot all the constraints from terrestrial setups to look for the scattering of dark matter coming in from the halo, this is the combination. Even this is not so complete, but this is representative. This is how the combination of all the constraints would actually look like. Okay, and notice that all these constraints from these various experiments are bounded on all 4 sides, as you expect, right? So, okay, why are they bounded? What is the physics behind why there are these boundaries? Here's a rough explanation for why there are these boundaries. Now, let's start with this direction, the south direction, okay? I cannot keep probing down to arbitrarily small cross sections. Why? Because the smaller the cross section, the less the probability of a transiting particle hitting the detector. So these particles, the dark matter particles down here, are behaving more and more ghostly, and they would just pass through the detector, and that sets my sensitivity here. So how would I beat that? I'll just try to build a bigger detector and wait longer, right? Larger exposures, basically. If I go in the western direction, why can't I go to arbitrarily small masses? Because there, my dark matter streaming in is now so light that it wouldn't transfer enough energy to my target nucleus to trigger the detector. Okay, so in other words, if my dark matter particle is lighter than about a nuclear mass, my dark matter behaves more like a bug hitting a truck as opposed to a truck hitting a bug, right? So the bug is not going to move the truck. That's what happens. So the truck doesn't care, right? So dark matter is powerless, and that sets the limitation here. And I'll try to beat that by building more and more sensitive detectors, looking for and trying to reduce the energy threshold of my detectors, making the detectors smaller, using lighter atoms and so on, lighter nuclei and so on. Okay. Now up here, unfortunately, I won't talk about that much, but it's one of my favorite directions. So the reason why you're limited in this direction is that if the dark matter cross section is too small for hitting on nuclei, too large, then the dark matter might scatter so many times in the earth or in the shielding of the detector before it gets to the actual meat of the detector, the fiducial volume of the detector, that the dark matter might just get slowed down by the time it gets to your detector. Okay, so the dark matter becomes tired and does not have enough kinetic energy to trigger your detector. And that sets this limitation up there. So this is called the overburden effect. Anything that shields the detector is generally called an overburden. And finally, in this direction, which is what we're going to focus on a bit today, if the dark matter mass is large enough, then remember that we only have a handle on the mass density of dark matter, not on the number density, right? So if I keep increasing the mass, the number density of dark matter decreases, Hence, the flux of dark matter going through your detector decreases. And there comes eventually a point where the flux is so small that I could wait for a few years in my I could basically wait for a few years, but then not a single dark matter particle would have gone through my detector in that time, leave alone scatter. Okay? So in this direction, ultimately you are flux limited. Dark matter is just so rare and dilute in the halo that you just don't even catch it, actually. You don't even see it transiting through. Okay, so those are the broad principles that set limitations on these detectors. And I would encourage students to any experiment that you think about. I highly encourage students to think about all the limitations. There's always try to think of all the 4 directions in which, if you have a coupling versus mass plot, think about what we usually see the upper bound, which is funnily on the lower side. But think about what sets the lower bound, which is the ceiling. Think about what sets the mass limit. Think about all the boundaries. It's always fun, and you'll learn a lot about it. Okay, and you'll really understand what the experiment is about. Now, this line, right? This was drawn by the Dama experiment way back in 1999, before they got into the annual modulation business, just when they were getting into the modulation business. But not many people actually think about this frontier, the high mass frontier, right? Only of late, the last few years, there has been a sort of a revival looking for super heavy dark matter in this region, looking for unique signatures of super heavy dark matter. Okay? Now, to give you some visualization of what's going on there, see, you could ask the question, is there dark matter in this room? Okay? That's an impossible, you cannot answer that question, because you need to first ask, what is the mass of the dark matter particle, which we do not know. The mass sets the number density, because you know what the mass density is. And the number density tells you what, the inter-dark matter particle spacing. So if dark matter had a mass of 100 GeV, then the typical interparticle spacing in the halo is about 7 centimeters, and you can be sure that the dark matter is in this room. In fact, dark matter is passing through your body right now. But if the dark matter mass is around 10 power 16 GeV, which is where the Dama had drawn their limit, then the number density is so small that the interparticle spacing is more than 4 kilometers, and you can be sure that dark matter is right now not in this room. You can be very sure. Right? So this is how you visualize what's going on in that mass range. So naturally, the question is, what if dark matter is here? What if it's beyond the Dama? Okay? Then what do you do? How do you set up? What kind of experiment would you set up to look for such dark? Now, thinking about dark matter in that mass range, it's not completely crazy. Okay, there is a lot of theoretical appeal to this. People have thought about it over the decades. Super heavy states appear ubiquitously in theories of grand unification of forces. And this is actually a woefully incomplete list. But there are many ideas out there in the market that make these kinds of dark matter particles in the early universe. Notably from Hawking radiation, of primordial black holes, through the Wimpzilla idea, which is producing these states gravitationally at the final stages of inflation, through preheating, and even through thermal model. Okay, although it's sort of a difficult model to arrange, you can have thermal mechanisms beyond the so-called WIMP unitarity limit as well. Okay, and there has been a recent wave of giving dark matter candidates in this mass range. We are producing heavy, strong, stable states. I'm not going to go through all these, but there are many more possibilities than I've listed here. This is slightly outdated, and I encourage you to go look at the Snowmass white paper that I coordinated with Daniel Carney that explores exactly this landscape. Okay, there's many models out there that give you exactly these large cross sections and large super heavy dark matter masses. Okay. Now, the relevant question for this talk is, so Dama back then in 1999, they used, as I said, a sodium iodide crystal that's about 10 centimeters in linear dimension, and they waited about a year to look for candidate events, right? But we know that today dark matter detectors have gotten much bigger. They're a meter in dimension, in linear dimension, and they wait longer also typically, right? So would that mean that the rarest huntable dark matter candidates have these detectors already secretly set a limit, and then we just didn't know about it because they didn't draw the line all the way to high masses? That's one question to ask. Another is, okay, fine. So there are dark matter detectors, but we know that there are much bigger detectors that neutrino experiments deploy. What about those detectors? If you have a much bigger detector, there is a much higher flux that you can admit, and hence much higher masses that you can probe, dark matter masses, right? So these are some of the questions that we explored. So this slide, I think, just shows you what are some candidate dark matter experiments that can do this. Using xenon, you have xenon 110 LZ Panda X. Using argon, we had just the recently decommissioned Deep 3600 experiment, and then you have bubble chamber experiments like the Pico 40L experiment. They all have a linear span of about 100 centimeters. Okay, so the question was, did these experiments already set a limit and they just didn't know about it, right? No, that's not true, because it's not that easy, okay? Not so fast, because there's yet another effect of dark matter scattering that must be taken into account to actually do a search for these kinds of particles, okay? What is that? I've shown that with this cartoon. If I increase the dark matter mass, clearly you're probing larger and larger cross sections to compensate for the decrease in the flux, right? So what happens is you'll eventually hit a cross section at the highest masses where the dark matter particle the detector becomes optically thick to the dark matter particle that is passing through. Okay? In other words, I will eventually get to a cross section where I expect a dark matter particle that is passing through to scatter multiple times as it passes through, okay, as opposed to just once. Because remember, a cross section is after all defined by its optical depth. The optical depth is the number density of the target times the cross section times the length that is traveled through. So if I increase the cross section, I will come to a point when I expect multiple scatters as it passes through, as opposed to just one, right? So that's a different beast in these experiments, as opposed to the WIMP search. In a WIMP search, you just look for a single scatter. Here, you're looking for a track. It's not even a track. It's like Christmas lights. Okay, hit. Okay, so to cut a long story short, to cut a very long story short, these kinds of searches, once we proposed that this search has to be done, they were done. I participated in the Deep 3600 experiment, my only experimental paper. Xenon 110 and LZ have also published results using this multiscatter search. At PicoL, there was a graduate student who did a search and published it in his thesis and so on. So multiscatter results have now been published. I'll show you the results in a while. Okay, but for this talk, we're going to focus on something a little more speculative. If these detectors can do it, why not these detectors? Why can't neutrino detectors also get into the hunt? Okay. Now, the first thing to note is that not all neutrino detectors can do this. Okay. The ones that use organic liquid scintillators, such as SNOW+, Borexino, and Juno, they are the detectors that are most suitable for this kind of direct detection search. Okay, and we'll see why. Because it all comes down to you just have to collect enough light in the PMTs within the dark matter transit time, and then you're in business. Okay. On the other hand, detectors that use water Cherenkov technology, like Super K or the erstwhile SNOW experiment, could not do this because dark matter is streaming in at non-relativistic speeds. It is not going to trigger the target particles above the speed of light in the medium, so we're not going to get Cherenkov signals. Okay, and finally, liquid argon TPCs like Dune are also not suitable, although there's an asterisk with that. We can talk about it offline, because the threshold is just too high, okay, to a first approximation. Threshold is about 5 MeV. Again, dark matter is coming in really slow. It's not going to trigger 5 MeV recoils in argon. Okay. All right. So, liquid scintillator neutrino detectors. Of course, as I mentioned before, the first thing you notice about them is that they're pretty big, right? So here's the xenon experiment, here's the borexino experiment, and here are physicists for scale, right? So they're standing right beside here and they're sitting on the detector here, near the PMTs, right? So what that tells you is that the fluxes of these detectors, of borexino in particular, is about 100 times greater than the flux, the integrated flux that you would get from xenon 1 ton. And that means just like that, your mass sensitivity is 100 times greater than xenon 1 ton. Okay? And as for the cross-section sensitivity, you just need to satisfy the selection trigger, which is the number of photoelectrons that the detector can see within a given time window. Okay, as long as you satisfy that, you satisfy the cross-section sensitivity, and then you are in business. Okay. So this is a couple of photos from my visit to Snow Lab, where I talked to the Snow Plus experimentalists about this, and they were glad to do this once they start taking data. Here's a scale model of Snow Lab that I took, because I couldn't really see the Snow Plus experiment. It was hidden from public. But here's a scale model of the experiment. Here's a selfie I took on one of their PMTs that they had put out for repair, which was 2 kilometers underground, by the way. Yes, one of the deepest particle physics experiment. Okay, now, what I had showed them in that collaboration meeting was that because they had a fiducial area of about 1 million centimeters squared, as opposed to 10 power 4 in dark matter experiments, if they were to do a search for just 3 hours, they would already beat the Dama limit. Okay? And if they were to do it for just 10 days, if they were to dedicate the detector for dark matter for just 10 days, again, they would all, in the mass frontier, they would already beat the sensitivity of xenon 1 ton. Okay? And if they waited a year, they would go past the Planck mass, which is totally fine. You're just probing some sort of composite dark matter. With 10 years, they would go to 10 power 21 GeV and so on. Okay, so this statement is actually no longer true. I had said, so this is, again, this is an outdated slide. This is not the first experiment to reach the Planck mass. The deep experiment has already done it. Okay, we've already set a limit at the Planck mass. Okay, but nevertheless, that doesn't take away anything from Snow Plus. You still would get some of the best mass sensitivities to dark matter. The highest masses that can be probed on Earth can be done. Okay, now how would dark matter actually look like in the Snow Plus experiment? Keep in mind that given that the dark matter speed is about 1,000th the speed of light, it would take about 10 microseconds for dark matter to transit a detector of this size. Okay, so your signal is nothing but a continuous deposition of photoelectrons over this transit time. Okay, that's mainly it. Okay, one other thing is that because you're dealing with dark matter that is so heavy, like upwards of 10 power 17 GeV if you want to beat the Dama limit, and because the target carbon is around 11 or 12 GeV, the path of the dark matter that's passing through is very, very, very close to collinear, right? The angular deviation would be really, really small, the level of 10 power minus 16 or something. So for all practical purposes, it would be a very collinear track with continuous deposition of energy. And since these experiments have excellent timing information, which leads to good vertex reconstruction, you could exploit these to look for multi-scattering dark matter and hence do actual direct detection. Okay. Now, here are, yes.
This one.
Yes,
so
yes.
This reminds me of the strategies experiments used to look for magnetic monopoles, for example.
That is absolutely right.
Similar? Can you distinguish between these two?
One can. So with magnetic monopoles, the distinguishing thing is DE dx, basically, DE over dx. With magnetic monopoles, it's higher actually. Whereas these are much lower energy depositions. Absolutely, yes. Okay. So here is how a few transit windows would typically look like. Okay, this I just generated using Poisson fluctuations in Mathematica. Now, over a 10 microsecond window, If I had a dark matter signal with a per-nucleonic spin-independent cross-section of 10 power minus 28 centimeters squared, this is how the window would roughly look like. These are just representative of hits I get in time. Okay, so with some random Poisson fluctuations, this is how my windows would look like. Whereas typical 10 microsecond windows in the Snowplus experiment would look like this. Okay, confusingly, these come from what are known as dark counts, which has nothing to do with dark matter. These are just the thermal agitation. These photoelectrons just come from thermal agitations of the photomultiplier tubes. Okay, they are called dark counts for whatever reason. So that constitutes the main background for this kind of search. And then typically, they look like this. So they're much more sparsely populated than my dark matter signal for this benchmark at least, right? Now, these liquid scintillators have some contaminants despite a lot of distillation. One of them is carbon-14. I don't remember the half-life of carbon-14, but what it would do is that, given the abundance of carbon-14 in the detector, 1 in 100 such 10 microsecond windows would look like this with the carbon-14 deposition, okay? But it deposits much higher energies than the dark matter signal. And then, even if I didn't have carbon-14, if I waited 10 years and then I took a lot of 10 microsecond windows, I'll have the look elsewhere effect, right? The trials factor, basically. So not all 10 microsecond windows would look like this. Once in a while, due to statistical fluctuations, even the dark count window will look like this, actually, as noisy as the dark matter signal. Okay, so that is the ultimate sensitivity killer for this kind of search. All right, so taking into account this trials factor, the carbon-14 background and so on, here is how the punchline plot would look like. This is the future reach of Snowplus in the cross-section versus mass space again. Okay, so if Snowplus were to implement their existing trigger, it's actually the trigger that exists in Borexino, which Snowplus wants to adopt. If they were to use that trigger, then this would be the sensitivity to dark matter at about 10 power minus 26 centimeters square. Okay, just below QCD cross sections. And with the 10-year exposure, they would go all the way to 10 power 21 GeV. But if they were to implement an improved trigger that takes into account dark counts and trials factor and so on, they can become more, they can improve their sensitivity by a couple of orders of magnitude and go down to 10 power minus 28 centimeters square. Okay, so I know this plot is busy. There are other constraints as well on this, but I don't want to talk about it now. Okay, but this space is where you would operate with your Snowplus detector. One little digression is there already has been a recasting of a search at a neutrino detector to look for multi-scattering dark matter. This was performed by Raphael Lang, Michael Clark, and a couple of others whose names I've forgotten, using the Majorana demonstrator. So Majorana is a germanium-based detector deployed or commissioned to look for neutrinoless double beta decay, right? But they had a prototype which is called a Majorana demonstrator, also using germanium, and this is how the detector setup looks like. They have all these, ice hockey pucks of germanium, and these guys basically realize that the energy sensitivity is good enough that if you have dark matter transiting through the setup and scattering multiple times on these different modules or nodules, whatever, then you could actually look for a dark matter track with the timing information they have. So they use that to basically set a limit on the dark matter versus cross-section versus mass space, and this is the limit that they set. Okay, so this has already been demonstrated that you could use some sort of neutrino facility to look for dark matter from the halo. Okay, so here is a summarizing plot of the first half of the talk. Here's again a bird's eye view with all the orders of magnitude in cross-section and mass. What I had not shown you before was this green area. In particular, this region would be ruled out by Snowplus in the future if they were to do an experiment. This sort of has been ruled out already. This is not quite accurate. Again, this is an outdated slide, but Xenon 110 has already performed a search for multiscattering dark matter, and around this region has been ruled out by Xenon 110. The deep 3600 dark matter experiment has also looked for multiscattering. So a lot of this space beyond the Dama limit from 1999 has already been probed. Okay, and Snow Plus would really change the game, by orders of magnitude. Okay, so since I'm going slow, I'll kind of rush through this. There's one fun thing that you could do if you started seeing these multi-scattering signals, okay, all right, which is to start saying something about the phase space distribution of dark matter in the galactic halo. Okay, how could you do that? Because since you have such good vertex reconstruction and timing information, you could, if dark matter, if you had a dark matter event, multi-scattering event through something like Snow Plus or Borex, you will, using which of the PMTs light up at what time, because you have excellent information on timestamps and so on, you could literally reconstruct the direction and path length of dark matter. Okay, so that tells you what the dark matter speed is. So literally, event by event, you could reconstruct the speed of dark matter to a very good precision. Okay, so what can you do? That means, because you've reconstructed event by event, you can now assemble your data. You have distributions of the dark matter speeds and the dark matter entry angles, right? And since you have these distributions, just like that, you can determine halo properties like the dispersion speed, the escape speed, and any anisotropies and so on. We don't know these things for sure. Okay, we only infer things from stellar kinematics and so on. But now, right here, right in your lab, you can reconstruct all the halo properties because your dark matter is literally leaving a track in your detector. Okay, and of course, if there are any velocity-dependent backgrounds, those also you can reject using this technique. So I'm not going to really go into how that can be done. Just take my word for it. Okay, statistics can be done. So I'm going to move on to the second part of my talk on how you could repurpose other neutrino facilities to look for a specific kind of dark matter known various in the literature as dark baryons, dark neutrons, hidden neutrons, mirror neutrons. They go by many names. Okay, so the first half talked about looking for scattering of dark matter in a more or less model independent way. Okay, more or less model agnostic. You just needed dark matter to have nucleonic scattering cross sections, right? Here we're going to talk about a specific model with very specific signatures. So what is a specific model? The hypothesis here is that we are introducing a new particle characterized by it having zero charge under all fundamental forces, standard model singlet. I'm going to give it a spin half, make it a fermion, and crucially, I'm going to give it baryon number 1. Okay. Now, if I just told you this, of course, you're going to say, or James Chadwick, the disgruntled ghost of James Chadwick is going to come up and say, what I've described is just a neutron, right? I've not said anything exotic here, right? Or if you want to play the flavor game, it could also be one of these baryons, the delta baryon, the sigma baryon, and so on, right? And James Chadwick would not be so wrong because what I have described is sort of a neutron. It's just not the standard neutron. It's a non-standard neutron. I could call it a dark neutron because we've not seen it. Dark in the sense of hidden, okay? And the only difference, literally the only difference now at this point between the standard neutron that we know and love and this dark neutron is that we know the mass of the standard neutron, whereas we have no idea what the mass of the dark neutron is. Okay, now if I put it that way, I have to write down a Hamiltonian like this with diagonal terms, but crucially also off-diagonal terms because nothing forbids it. And if I have off-diagonal terms in the Hamiltonian, I cannot help having quantum mixing. Quantum mixing is also not new to you. You would have seen a very crucial part of it in this conference, which is, quantum mixing leads to oscillations among the neutrino flavors. Right? Andre must have surely imparted that to you. Quantum mixing is also very ubiquitous. We know that the photon mixes with the rho meson, photon at high energies mixes with the Z boson, and so on. Right? Now, some interesting consequences for neutrons mixing with these dark neutrons would be, you could also have neutron oscillations, right? Oscillations of probability for detecting something as interaction eigenstate as it propagates, correct? So you could have neutron oscillations so that I could throw a neutron. So now I've switched from a cricket analogy to baseball analogy because we have Americans in the audience. So you could throw a neutron at a wall, and then the wall could detect it as a dark neutron sometimes with a non-zero probability and let it pass through, and then by the time the batter picks it up, he or she measures it as a neutron again. Okay, so I can have neutrons shining through a wall due to this oscillation, just like photons shining through a wall or whatever, right? Light shining through a wall. I'll also have a magnetic, okay, this is not so important, so I'm not going to get it, but neutrons have a magnetic dipole moment, but now I have another state, so I can have a transition dipole moment. Instead of a neutron, I can just switch it with a dark neutron, which we won't get into too much in this talk. Okay? Okay, so why do we care if this hypothetical dark neutron exists in the Lagrangian of the world, right? Why do we care? Well, this could very well be the dark matter of the universe. In many scenarios, this dark or hidden neutron is cosmologically long-lived. It ticks all the boxes for dark matter. And we did some cosmology calculations and showed that it generically has abundances comparable to baryonic matter, which means this could very well be or a large fraction of the dark matter of the universe. Okay? And for this talk, there are many other motivations as well, but I'm just going to stop here as far as the motivations go. Okay? Now, okay, let me skim through this quickly. Now you might ask, where do these dark neutrons come from? Dark neutrons could either be elementary or composite. Okay, we know that neutron is a composite, a QCD composite, but dark neutrons need not be composite. There's at a hadronic level, I can always write a Hamiltonian like this, and with an off-diagonal mass with the neutron, and again at the hadronic level, if I write this inevitably, I'll have a transition dipole moment, which I talked about earlier. Okay, it has its own interesting phenomenological consequences, but not for this talk. And then you might ask, okay, at the hadronic level, that's the Lagrangian. How do UV complete it? Ben Fornal and sorry, Nick, I forgot Fornal's first name, but Ben Greenstein and Bart Fornal wrote down this UV completion. They were the ones to actually popularize dark neutrons, where they show that using a diquark, talking to both the dark neutrons and the quarks, you can UV complete it, and you have all sorts of interesting things going on. You can explain the neutron lifetime puzzle and so on. Okay, which again we're not going into today. And as I said, the dark neutron could be a composite as well. One realization among many is for this composite to arise from a mirror sector. Okay, so I'm not a big fan of the mirror sector, but this seems to be a popular one in the market, where you have a mirror sector literally, which is right-handed counterparts and other states of the standard model with its own mirror Higgs, which gets a vacuum expectation value of its own. People have been thinking about this for a long time. But of late, it has taken a revival in the form of neutral naturalness in twin Higgs realization to explain the naturalness problem in the electroweak sector. But more pertinent to what we are doing here, the neutron in the mirror sector, the mirror neutron could now actually act as the dark matter of the universe. Okay, and mirror sectors also feature ubiquitously in baryogenesis mechanisms and so on. Okay, so this is just to satisfy the question, where could these dark neutrons come from? They could come from many places. Okay, for now, let's just think of the phenomenology of what happens if we have a dark neutron in the Lagrangian of the universe. Okay. Okay, so now, if the dark neutrons make up the dark matter of the universe, which they can, generically, okay, if they are long-lived enough, then just like neutrons get absorbed in nuclei, I can have the halo dark matter, the halo dark neutrons absorbed in nuclei again, because this is just through quantum mixing. Right? I just have to insert the mixing angle, and then it behaves like a neutron, right? If it's in the right mass range, right? So using that fact, one could set limits on the halo dark matter from nuclear absorption, especially in large volume detectors, which happen to be neutrino detectors. Okay. Now, notice that so this is the off-diagonal mass that I showed before. Notice that this is also at a very, very small scale, right? Electron volts. Okay, this is where you usually set limits. And this is the mass splitting between the mass eigenstates of the neutron and the dark neutron. Again, notice that these masses are psychotically tiny. This is in electron volts, and I'm talking about 10 power minus 10-ish electron volts, right? But nothing really stops you from doing that in phenomenology. Just indulge me. So what happens? I could use experiments that looked for neutron absorption at very large rates and use them to set limits on dark neutron absorption from the halo, right? For instance, neutrons at the erstwhile SNOW experiment, right, who had the best solar neutrino data, one of the best solar neutrino data. One of the things they looked for is neutrons, hitting deuterons through a quasi-elastic process and converting to neutrons, neutrinos, and protons. And the neutron that you produce in the final state gets absorbed in the heavy water, and that's how you set a limit on that's how you measure the flux of the solar neutrinos. Okay, through this elastic process, and this is the rate, the integrated rate that they quoted. So one can make use of this, and then I can take the flux of dark matter coming in, appropriately insert my mixing angle. I know what my neutron-proton scattering rate is, right? If I imagine that it's actually neutrons that are raining in instead of dark neutrons, I'll just remove the theta square. Imagine neutrons are the dark matter. I'll just have phi times the cross section, but I have to insert the theta squared. And so comparing these rates, I can set a limit on the mixing angle and mass, right? The mixing angle, which gives limits on the off-diagonal mass and the mass splitting, right? So that's what this is. SNOW, yeah, here it is. Okay, the brown region. Similarly, I can make use of another search that looked for neutron absorption. This was in the Borexino experiment. They did a slightly crazy search looking for carbon-12 decaying to some exotic carbon-11 state via some Pauli exclusion principle violation. Let's not get into it. But the key is that they also looked for neutron absorption. So I can piggyback on that and set a limit again using the quoted limit on the rate at which this happened with their exposure. So I get a limit that's kind of comparable to SNOW+, but also complementary. Okay, so good. So absorption can be done using neutrino detectors. Now, how do I do neutrons shining through a ball with this setup, right? So I talked about what that was. This is a kind of a cartoon of what you can actually do in an experiment. You could, if you had an intense neutron beam that was well shielded, especially shielded, the shielding is designed to absorb neutrons, then if I had another detector down the line that could, a neutron detector, right? Then if I have neutrons converting to dark neutrons and regenerating, basically I can look for excess neutrons in the detector, right? So that's the idea, and it so happens that there is an experiment that can very well do this. In fact, they could be the most sensitive experiment to this kind of setup, and that is the ISODAR experiment at Fermilab in Korea, okay, about 1 kilometer underground, okay? So here's sort of a busy slide. So ISODAR, the main goal of ISODAR is to do neutrino physics, okay, is to get some measurements on neutrino oscillations. So what they actually wanted to do was, so here's the setup. You have a proton beam Okay, in a slightly weird way, it goes around and turns around and then hits a beryllium target. And then you produce a chock full of neutrons, which is QCD crap, right? And then these neutrons get absorbed in a lithium-7 sleeve, just around lithium beryllium, but mostly lithium, a lithium sleeve that's just around the target, the beryllium target, so that the neutron gets absorbed in the lithium-7 and produces lithium-8. Lithium-8 immediately beta decays to beryllium-8 and importantly electron antineutrino. Okay, so that's the key. This is the roundabout way for them to produce many electron antineutrinos. Once you produce electron antineutrinos, they have a large liquid scintillator detector downstream, a few meters down the line, and then they're basically looking for the appearance of electron neutrinos itself. Okay, the anti-electron neutrinos, electron antineutrinos. Okay, so that if you have oscillations, then you will lose some electron antineutrinos, and they'll be able to measure that. Okay, so now we can piggyback on this setup. What are we doing here? We only care about the neutrons that you produce here, and then the neutrons, as I said, convert to dark neutrons, come out, and if the neutron itself gets into, if the neutron reconverts here, okay, so the n prime is the dark neutron. If the n prime gets into the detector and hits one of the detector particles and converts to a neutron, the neutron will thermalize a bit, take a random walk, and then get absorbed into the hydrogen or the carbon in the liquid scintillator, producing characteristic gamma ray energies, right? So without without changing the setup, one could parasitically make use of isodar and set some of the most sensitive limits on the space of the off-diagonal mass and the mass splitting. Okay, that's what this is, the gray bands. The band represents some uncertainties in cross sections and where you want to put the detector and so on. Okay. Okay, I'm not going to go through the calculation because we don't have the time, but yeah, it can be done. You can calculate the probability for this conversion to happen and so on, account for oscillations in the medium, etc., etc. Okay, there's yet another limit. Very quickly, you can bottle up neutrons in what are known as ultra-cold neutron facilities, and then you basically look for neutrons that are disappearing again through this neutron through shining through a wall kind of setup, and then getting an excess of neutrons disappearing on top of neutron decay would help you set limits on the dark neutrons. And finally, more relevant to neutrinos, there are already searches that do this kind of neutron shining through a wall experiment using reactors, basically. Okay, so these are nuclear reactors, but these are not commercial reactors. These are reactors meant for science. This one is stereo in Paris, I believe, and again, they basically have I forget what the source is, but they basically produce a very intense flux of neutrons, and then the neutrons are led to regenerate through heavy water and through the concrete, and you have these detector polythene detector modules in which you can detect the neutrons that got regenerated. Okay, and they set a limit that looks like this. Okay, now these limits look close by because, as you know, any shining through a wall experiment, the sensitivities go as 4 powers of the coupling. So I can only set a sensitivity that is 1/4 of the rate in the power, and that's why it looks like they're all close by, but the rates are really widely separate. Okay, so here's like a quick summary of all the kinds of experiments one could make use of. I mentioned isodar. There's also another dedicated experiment called HFIR that looks for this kind of neutron regeneration. You could make use of atmospheric neutrons to do this, just like I did dark neutron, dark matter from the halo. So they all have various sensitivities depending on what the resonant energy is and so on. But the best seems to be the isodar experiment. Okay, the best sensitivity seems to be given by the isodar experiment. Okay, so I'm very close to my time. Okay, I usually show this when I give dark matter talks, just to say that that dark matter is non-luminous, ubiquitous, plentiful, but everybody is making valiant efforts to look for it, and one cannot help feeling hopeful that pretty soon it will stop being mysterious, and then we'll start to learn what it really is. Okay, so okay, I'll just end there, and I'm happy to take questions.
This is regarding the local dark matter density. What is the error bar in it?
100%. So it could be, so I said 0.3 GeV per centimeter cubed, but depending on who's doing the fitting, it could be 0.6 all the way down to 0.1.
So the other question is, will there be any attempt to future way of improving it other than stars motions, observing it? Because our calculation is highly dependent on how much that local dark matter density is there.
It is dependent up to a factor of 2. Absolutely. Canonically, people take it as either 0.3 or 0.4, but it's not more than a factor of 2 actually. And on for example, in a plot like this, where I'm showing many orders of magnitude, you almost won't see it that difference. But yeah, I'm not aware of. So there are continuous campaigns to keep improving on this measurement. People, as astronomers, are doing this, and I believe Gaia is also trying to do it for the local. Gaia people also for the local solar vicinity. But yeah, things have to improve. Yes.
So as the mass density keeps decreasing, you said number density keeps increasing. So is there any limit on that number density, upper limit?
So upper limit on the number density. Yeah. Okay, so that would mean, okay, now I'm getting confused about what is upper limit. If you're asking about what is the highest number density I can go to.
Yeah.
Okay, that would come from considering what is the lowest mass of dark matter I could think of. And that is around 10 power minus 23, 10 power minus 22 electron volts.
Okay, then we can relate the number density.
Yes,
yeah, okay.
From there you can get it, yes.
So is there any mass limit on this neutron dark matter candidate?
Yeah, okay. So the mass limit, I don't know. Yeah. Okay. So these are some of the limits. These are just some of the limits, okay, from nuclear absorption. But I think I have a backup slide on other limits as well. So in all this parameter space, especially on the left, sorry, not on the right. Yeah. On the left, this is all where the dark neutron could be the dark matter, and here are the limits basically, right? So okay, to be to go a little slow, these limits basically come from considerations of cosmology and heating of neutron stars and other things, and you get this as the limit. And then over here, where I have the dark neutron heavier than the neutron can decay to the neutron. And so it looks like it need not be the dark matter, except if I satisfy the bounds on dark matter decay, that is if my dark neutron decay lifetime is larger than 10 power 25 seconds, then it can be the dark matter. And that is what I'm showing here. So anything below this yellow line, it could be the dark matter. In that case, there is almost no limit actually. There's almost no limit to how heavy it could be.
So if
I can keep going as I keep going down to, I can keep going to the right as I go down to.
So if the mass of this dark neutron is less than the mass of the proton, then
yes,
the proton can decay in this particle, and then we can get the
just
limit.
Less than the proton. Not just, I mean, it has to be, the proton has to go, so proton minus electron, or proton plus electron. Yeah, correct. So that's one limit. You get a slightly better limit by looking at the stability of beryllium-9 because of the way the nuclear binding energies work out. Slightly better limit. So that's what I've drawn here. But the proton limit looks more or less like this. So that is what this limit is, the limit that you mentioned from proton decay.
We can put a lower mass limit from the proton decay experiment on the.
That's what I'm saying. Yes. So that limit would look almost exactly like this.
Yes.
But it so happens that the beryllium-9 stability gives you a slightly better limit than the proton decay.
Hello. So when we consider this ultra heavy dark matter,
yes,
it can happen that this is not the total dark matter content of the universe. It may be a fraction of the dark matter. So, but when we consider this number density, we consider this rho by m chi, right? Which is the total dark matter density.
That's right.
So is it possible to assign a limit on this fraction somehow?
100%, yes. So when you see plots like this, right?
Yes.
The intrinsic assumption that goes into this is that it is whatever it considered the particle that you assume that's interacting with the detector constitutes all the dark matter. If you relax that assumption, all these limits will get relaxed proportionally. So if I'm thinking of 10% of the dark matter made up of this particle, then all of this will go up by factor of 10. This will shrink by factor of 10 and so on. So one can consider that, yes. One should actually, yes.
So there is no limit on that till now.
No, not really. I mean, there's no, we can't say that.
Because there are already two unknown and.
Exactly.
Thanks.
That's a third unknown, exactly, yes.
Hi, actually this is the little bit supervision of that previous question. Like if dark neutron is the dark matter particle, then what will be the relic density corresponding to that one? Like, will it be 0.12 or obviously not, I think.
Okay, so I don't have a slide on that, but actually, yeah, we did an entire project on that actually. So when we did these calculations, that's just what we were trying to determine. Generically, what would, okay, I can call it a relic density. Through number changing processes, because I have processes like these, right? The neutron going to chi, gamma, and so on. Through these number changing processes, can I keep the chi, dark neutron, in chemical equilibrium with the baryonic fluid? And it turns out that as long as the reheating temperature is higher than a GeV, which is far from crazy, as long as I have that, and as long as my mixing angle is larger than around 10 power minus 20 or 10 power minus 15, then the dark neutron abundance turns out to be, there will be chemical equilibrium, and then it will be comparable to the dark matter abundance. So it can make up 1/5, at least it should make up 1/5 of the dark matter.
Okay, like it will be not the 100% one, but it's like one.
Yeah, it can be. Yeah.
Okay.
Yes.
When you showed in the first part of your talk, you were showing the plots of dark matter nucleon cross section versus the mass.
Yeah.
So in those plots, what is the assumption that we take? How does the dark matter interact with matter?
So the assumption, there are not too many assumptions that go into it. For this kind of plot, one assumes that first of all, when I show this plot, I'm assuming that the scattering is spin independent. Also, it is velocity independent. That whatever Lorentz structures I have that give you the interaction, don't give me a velocity dependence in the numerator or denominator in the cross section. So some sort of contact operator, scalar bilinear interaction.
So
an elastic scattering. So these are the elastic, velocity independent, spin independent.
It's mediated by weak interactions?
Need not be. Anything, yeah. In fact, yeah, if you say weak with a capital W, like really weak, electro weak, then that's rolled out already, right? Because I expect that cross section to be 10 power minus 39 centimeters squared in the electro weak mass regime.
So basically 2 questions. So now there should be some dependence on the coupling strength also and the form factors of the neutrinos for that interaction.
That's right.
So how do we estimate?
Okay, so all of that goes into computing your rate from your theoretical side. So you have a constraint on the rate experimentally. If you want to set a limit on this cross section, then you take the differential cross section, you put the form factor, put the other.
So what is the form factor that we put there?
People generally use the Helm form factor. It's called the Helm form factor for coherent nuclear scattering that captures the loss of coherence. Yes.
And the dark neutron that you were showing, that is electrically neutral, and like if I think of it as an elementary particle, then where does it come in the standard model Lagrangian?
It doesn't. Why doesn't it come?
It doesn't come.
No, it doesn't come. No.
It's just a mixing between the neutron and.
Exactly. Yeah.
Thank
you. You mentioned this background from C14 for very heavy.
Yes.
Is that irreducible or is that can be identified and removed?
It can be identified and scrubbed out because I forget the numbers. So the dark matter, a single scatter will deposit around 10 keV because the carbon is 10 GeV. I have to multiply by 10 power minus 6. Whereas this will deposit around 40 or 50 keV. That's how I remember. I remember it's much higher than the dark matter scatter. Yes, yes. And it's localized to one place and it's 40 to 50 keV. So you can scrub it out, yes.
I don't see any other questions. So let's thank Nirmal again and break for coffee.
Thanks.